Fairchild CCD. It's a 62mm square CCD. It plugs in right here to the top of the camera, which I can tilt to show you. So it'll plug right on top of this copper cold block. The body of the camera is a vacuum weldment, different ports for different things, the cooling system, vacuum gauges and pumps. The electronics there'll be a connector right here that'll go directly to the electronics box, which controls the CCD. On the screen here is a AutoCAD rendering of the Sinistro camera, which is the main camera for the 1-meter telescopes. Up this top portion is the camera, the bottom box will be the electronic control. The main CCD chip is a Fairchild 4K by 4K chip. Right now our prototype will be cooled using a Cryo Tiger. We have the vacuum gauge, a vacuum pump, and an ion pump. Everything is designed here at LCOGT.
Hey, I am the designer of the latest controller boards for the Fairchild 486 CCD controller that LCO is designing. And what I have here is the latest incarnation of the boards that make up the controller. There are three basic functionalities of a CCD readout controller. One is an ability to generate clock signals. One is to read back the analog outputs of the CCD output. And the third is the brain to control the timing of either the clock's channels and the A to D readouts from the CCD. So this is running a benchtop camera right now. It's a small CCD, but it is made to built to read out this the Fairchild 486 CCD, which is a 4K by 4K 60mm square detector, and this is the electronics that will read that out. Some of the advantages of why we're making a CCD controller ourselves is for speed. We are attempting to run this at 4 amplifiers at 1 megapixel per amplifier, which will run a 4K by 4K CCD. We'll read it out at 4 seconds, which is a megapixel per amplifier. So we also have a very flexible binning that will do square and or rectangular binning from 1 by 1 up to 8 by 8. The electronics are designed to be scalable to a mosaic of 4 CCDs. Our optics in our telescope are able to support a larger field of view than a single CCD, so we can sort of multiply this by 4 and be able to read out a 16 amplifiers in parallel. We are able to read back and program all the voltage levels that you would want to change within a CCD controller to be able to optimize its performance. That includes all the clock levels, all the bias levels, and then we are also able to read back all those levels, as well as the output of the CCD voltage and the temperature of the electronics themselves. Some of the ways that we're able to get the performance that we're interested in is we have gone to somewhat novel style of electronics. One of them is that all the electronics are DC coupled from the CCD to the A to D, which enables you to be able to do a complete readout with no analog switching during the readout, which is a very important part of being able to have a very high fidelity readout. along with that, we are doing what's called digital correlated double sampling, which means we're able to simply digitize the output of the CCD as opposed to other styles of correlated sampling. Is we were able to take between 2 and 256 samples per pixel, which is a way of being able to digitally filter the signal, and so you're simply oversampling it at 4 or 6 or 8 or 256 samples, and able to filter the bandwidth that for noise. So what it does is it gives you a very consistent trade-off between speed and noise as you go from very fast readout rates to slow readout rates. And since it's all digital, you can choose the amount of filtering and the shape of the filter via the software. Other things that we've done to the electronics is that it has switchable front-end gain, so that you can just prior to any of the other electronics gain up the signal when you're in a 1x1 mode, a non-binning mode, and then you can drop the gain down by a factor of 4 for 2x2 binning, or bigger binning beyond that. Additionally, there is active load circuitry on the CCD output, which maximizes the output gain, which minimizes your noise. So there's a few items that we've had the opportunity to be able to put in, and so far they are all working as expected, and we are quite excited about where this is going to take us in the next few months.
Simply put, the purpose of an astronomical telescope is to gather light, collect it on a detector, tell you where it came from, when it got there, how much is there, and what color it is. The heart and soul of any instrument is the detector. This device, this is a CCD, the one we're going to use in the Sinistro Camera on the 1-meter telescopes. Its purpose is to tell you where the light came from by telling you where the bright spots are on the sensor and how bright it is, by converting the light to charge and then the charge to voltage and measuring that inside the controller. For this to operate properly, it needs to be kept about 100 degrees below freezing Celsius and at a very stable temperature, let's say 1,000th of a degree. Everything that we do inside the camera, the purpose of it is to keep the CCD at that constant temperature and protect its electrical signals. In order to cool the detector to 100 degrees below zero, we need to insulate it very well. We do that with a vacuum. It's about 100 billionth of an atmosphere, and that requires us to do all of the assembly work for the camera inside of a clean room, creating an ultra-clean environment inside the camera for the detector itself. In front of the camera, we put a shutter, just like you'd find in a typical digital camera. In our case, that shutter is a precision shutter that allows us to time exposures from, say, 1 millisecond up to basically an infinitely long exposure. Inside the Sinistro camera, we're actually using a disc-type shutter that has pieces of pie cut out of it for a narrow piece for short exposures and a wider piece for longer exposures. In front of the shutter, we put a filter changer that contains up to, say, 24 filters on Sinistro. In each of these filter positions, we put a different color filter. Like in your digital camera, you'd find a red, green, blue. And that's basically what we have in Sinistro. I've got a green filter here. These are just more precisely defined colors. We've got red, green, blue, but it might be just a different shade of orange from what you'd find in a camera. With the camera, we make every effort to determine how many photons, how much light is hitting the detector. We do that as precisely as we can. With the shutter, we make every effort to determine when those photons got there. We want to be able to time precisely when the exposures are open and shut. The minimum practical exposure time is really about 100 milliseconds, but we can time that to, say, plus or minus a tenth of a millisecond. Filters, we determine what color the light is. Those filters are characterized to, say, plus or minus a tenth of a nanometer. The last remaining element is to determine precisely where the light comes from. Now, if we can get the light hitting the CCD stably, then we can determine precisely where it came from. And so ahead of the camera, ahead of the shutter, ahead of the filter wheel, we have 2 pickoff mirrors in the instrument that allow us to feed the light without going through any of this extra instrumentation, we can feed the light to precision autoguiders, which are designed basically as higher frame rate cameras with their own little filter wheels and focus mechanisms. They're designed to precisely hold the telescope in the same position optically on the sky, not necessarily to an encoder feedback based on the ground, but to close the loop between the telescope position and the sky position. And if we can do that with the autoguider, then the light stays hitting the CCD in the same place, and we can precisely measure where the positions of the stars are relative to